Okay, so next again about the volume. So we have the solid, which is based on the given equation in 3b. Okay, so we have z equal to y square. We have z equal to 0 and x equal to 0, x equal to 1, y minus 1, y equal to 1. Okay, so as you can see here, all the 1, 2, 3, 4, 5 equations, they are all a plane, a flat plane. Okay, but then we have something curvy, which is given by z equal to y square. So first we have to sketch the trace so that we have an idea. So we have z y square, where the trace is on zy, we have the quadrant. Okay, so then when we sketch the surface becomes in 3D, it should be a surface. So let's say here I have the zy and this one is x. So now sketching something like this, and when we do a projection, we have this one, and that is the surface. Okay, but then the surface is bounded by x equal to 0, x equal to 1. Okay, so now if you look at here, so zy squared is the surface, right? And then when z equal to 0 should be the floor. So what we can have here, so that is the floor. So actually it can be extended to you can extend your graph. Okay, so it's very this one. Okay, so that is your plane. And can be extended. Okay, this is very, very long, but then it's limited by the okay, now we look at the on y-x plane, because they provide you the 4 lines. It looks like it's become boundary on the xy plane. So y, x. So you have x equal to 0, x 0, and then x equal to 1, this one, so this is 0, and y equal to 1, so this is y equal to 1, and then this one is negative 1. So it looks like you can so this one, let's say okay, x, so your x is always positive, so meaning that you don't need to extend, because you can see here if this is your region, it looks like this one becomes your region on xy plane. So your x is between 0 and 1. So let's say this one is supposed to be 0 and this one is 1, so we don't need to extend the length of this like the surface looks like a drain. Okay, so we don't need to expand. Just stop till x equal to 0. Okay, and if you can see, there. Your y can be positive, so this is the highest. Y is 1, and the smallest y you can extend this one is minus 1. So that is y minus 1. Okay, so it looks like when I redraw, so maybe I should redraw. So the y, this is y, this is x, this is 1, this is negative 1, and this is 1. Okay, so this surface, so I do the projection. So also I have the 1 here, and then negative 1. So I should have a quadratic, and that quadratic stop at that point. Okay, maybe I should correct my sketching. It's not so, sometimes it's not easy, I understand that, but you have to practice. Okay. Then your lower bound, so okay, so again, what is actually our solid looks like? So the solid is bounded by the z equal to y squared. Okay, when this is z equal to, so this is z equal to y squared, which is also this one, and then all the line y minus 1 to 1, x 0 to 1. So it looks like your solid is actually this one. Okay, so that is your solid under the quadratic, under the drain shape, or below the drain shape. So now we want to evaluate the volume of this solid. Okay, remember your solid, it should be closed and bounded. So that's why we don't choose the sketching over the quadratic. Okay, but we choose the under the quadratic or below the quadratic, which is we want to make sure it is bounded and closed by all these lines. Okay, so we have a z0. So where is z0? So z0, I've forgotten to mention. How can we have this particular shape? Because we already have the z0 and x0. So where is x0? So x0 is the surface behind here. So it is closed, right? And also z0 is the floor down here. The floor down here. So that's why we have this particular solid, okay, under the quadratic or under the drain. So now based on the question asking for finding volume using triple integral dv. Okay, so now you have to determine what type of solid that we have. So as a normal person, you will standing like this, right? This one. Or if you choose you yourself over here, so what is the plane that you are standing on? You are standing on xy plane. So in this case, we have xy solid, where your dv is dz, dA. Your dA can be dy, dx, or dx, dy. Okay, so now look at your limit of z, where the limit of z, you can see that from your solid that you sketch. Okay, based on these small people like you yourself standing inside that solid. So who is covering you, or who is becomes your floor? So your floor, because you're standing like that, where parallel to Z, so you can see that Z equal to, so your lower bound down there, Z equal to 0, isn't it? And who is covering you? The surface that covering you is part of the adjoint shape, which is given by Z equal to Y, which is this one, which is this, what this one, okay, which is this surface, right? This covering you, isn't it? Similarly for the other side. Okay, so you can say that the surface that covering you is belongs to, this surface is belongs to Z equal to Y squared. So you can put the upper bound of U is Y squared. So now we have the limit for dz. Okay, dz. So 0 to, sorry, the first, not this, the last. So 0 to Y squared. So now about your dA on xy plane. So what is your region looks like? So your region on y-axis plane is this one, which is part of your trace, where you can get it from this information. So you can see a rectangular region, right? Meaning that your dA, the limit of x and y, they are all constant. Okay, so now dy dx, or you have dx dy, and since they are all constant, so we have no issue here. So let's say you want to have let's say dy dx. Okay, so x, what is the limit of x and what is the limit of y? Okay, so now look at your rectangular region. So x is lying 0 to 1, y is minus 1 to 1. So your order dy dx, so what we have just now, x constant. Oh, can be because they are all constant, so it doesn't matter. So x is 0 to 1. You want to have dy dx as the outer integral. So x is 0 to 1, y is negative 1 to 1. Okay, so then we can evaluate that. Okay, so even though it looks like you have if you look at from your solid, do we need to split the region? You don't need to split the region because your upper bound and lower bound of Z, they are the same. You can see that even though you are standing on the x, y, Z positive, okay, so when x positive, y positive, so your upper bound and your lower bound of Z still 0 to y squared, right? So in this case, we don't need to split the region into two. I mean, we don't need to split the solid into two parts because all of them have the same lower bound and the upper bound. Okay, so okay, then because the integral is 1 because we are computing the volume of this particular solid. So then we integrate respect to z. We got z and substitute the limit, and it reduced to double integral, and after that we just evaluate. We will get 2 over 3 unit cube. Okay, so from the previous example also we need to put the, just to differentiate, I mean to make a difference, because now we are discussing on volume, then you have to put the unit cube. Okay, similarly for this one, you also have to put the 2 over 3 unit cube because we are computing the volume of the solid.